Okay, so we'll talk a bit more about graph theory today. Yeah, so let's take a look at number 2. Well, so first we need to say what an R regular graph is. So, if you can, it just says a graph is R regular if all the degrees of each vertex are, degree R. So, yeah. So maybe I should draw an example. This would be a 2 regular graph because all the vertices have degree 2. This would be a 3 regular graph because all the vertices have degree 3, and so on. 2 regular, 3 regular. You could have another let's see, maybe this could be another 3 regular graph where there's no vertex there. It's just 6 vertices, but the edges happen to cross. There's no vertex in the center. Okay, so yeah, I'll just let you guys think about number 2 for a bit, and well, or you can we can discuss it together, I suppose. So if it has exactly 20 edges and it's an R regular graph for some integer R, what are the possible number of vertices? So yeah. So yeah, what if R equals 1, right? If it's 1 regular, how many vertices will it have? So that means each vertex has degree 1. So the only way each can anyone describe what each vertex has degree 1, roughly what that would look like? Yeah, so Alan said 20 pairs. Yeah, exactly. So you have 40 vertices and you just kind of pair them up. So we'll just pretend there's 20 of these. And this would be a 1 regular, and there would be 40 vertices. And then, what are the other possible values of R or N? So let's see, what if R is 2, right? If it's 2 regular, yeah, so Elias says all integer factors of 40. Yeah, so well, let's check, right? Maybe not every one of them works, but that should be the right idea. So, if R is 2, then, one way it could look like is we could just have a length 20 cycle, right? I'll draw length 8, but pretend there's 20 edges there. So that's 2 regular, 20 edges. We'll just pretend I drew 20 instead of 8. How can we see that it has to be a factor of 40 though, for the values of N, I suppose, or R? So claim factors of 40 or conjecture or something. So, one way is we can count the total. What's the sum of the degrees of all the vertices, right? Well, the sum of all the degrees, if there's 20 edges, each edge, contributes 2 to the total sum of all the degrees of all the vertices. So sum of degree of V for all V in the graph is 40. Maybe I should write that a bit bigger. Sum of the degree of all vertices for all V in G is 40. So, if it's R regular, then, it has to be a factor of 40 then, because each vertex has the same degree. So, okay, so, we could have 2 regular, that works. And then N is 20. If R is 4, then N would would be 10. And we should check that we can actually construct such a graph, right? So I should have written this here on n equals 20. So let's see, I guess one way you can construct well, you guys should do the hard work. So how can we, draw a graph with r equals 4? Okay, so Sonak said we need vertices to be less than edges. Well, what do you mean by edges, right? Yeah, you mean degree, right? Not edges. Yeah, we need r to be less than n. So yeah, we should have the degree of each vertex is less than the number of vertices. So not all factors of 40 work, but about half of them do. So, for r equals 2, a cycle works. For r equals 4, we could potentially have, well, let's see, right? One way is we could just draw a disconnected. It could be 5 pentagrams. So just, there's going to be 4 of those. 4 pentagrams. And here's each vertex has degree 4. Let's check, r equals 5. Then let's see, how can we draw r equals 5? So we might need 8 vertices. If I drew in, okay, yeah, so we can take what's called the complement of this graph, meaning everywhere there's an edge here, we don't have an edge in the complement, and everywhere we don't have an edge, we do have an edge. So from every vertex, we draw the 5 diagonals, and we don't draw any of the edges of the octagon. And then each vertex will have, degree 5, because it's connected to all 5 of its non-neighbors. And then it'll work out to be, 5 regular, and it's fine. Okay, so this just means the path on 8 vertices. So complement is just, the complement of this would be this, because you just draw an edge with, it's just flipping whether there's an edge between 2 vertices or not. That's what complement of a graph means. So yeah, and then I think that's about it, right? Are the solutions always going to work for these split regular polygon-like shape objects? That's a good question. I think you can always force it to work, right? Like there are other solutions, because like for 2 regular, instead of having a regular 20gon, we could also have like just a bunch of we could just have a bunch of cycles, right? And just make the number of edges add up to 20. I think I drew too many. So 4 cycles would work, or a 20 cycle would work. But yeah, in general for the problem, I think you can't always make it work, because like, let's suppose the sum of the degrees of all the vertices is like, some integer, right? Maybe it has some like 100, I don't know. And then you want to find, so, there's 50 edges and the sum of the degrees is 100, for example. So, we try all factors of 100, and the way you can make it work out is if you arrange them into a like a cycle, then you can always make this like, let's say there's k vertices in a circle. You can always connect, vertex, like let's label it 1, 2, 3, 4, ... to k, and take the vertices modulo k. So if you want there to be r regular, you can just like connect 1 with like the 2 clockwise, the r clockwise nearest neighbors of in the circle, assuming r is less than k. And then you do the same for, actually, maybe this doesn't work. I think you should connect this to maybe about r over 2, like r over 2 of the next nearest neighbors. So, maybe like, let's say there's a 20 gone, and you range it 20 vertices in a circle, and it's part of our graph. Maybe there's 40 vertices total. If I connect this with if I connect vertex I with I plus 1, I plus 2, I plus 3, then I think this will be 6 regular, because, we also have that there's 4 vertices coming into I. There's this one, there's that one, and there's that one. Because, I minus 3 will connect to the next 3 vertices modulo, however many there are in this cycle, modulo k. So yeah, if you just connect the vertex with the, with I suppose like r over 2 vertices of its nearest neighbors in a circle, then it would make degree r. Or half of them might be on this side, half might be on that side, I guess. If r is odd though, I think you can fudge it around so that, maybe you have like the long diagonal, or actually the long diagonal wouldn't exist, but I think you can probably come up with a similar construction. I need to think about, that's a good homework exercise to think about if you can do it for r being odd. If you can always do it for r being odd in all of these like subgraphs. Okay. So, there's like some exercises on, can you construct a graph with these as the degrees of the graph? But we're just gonna skip those and not worry about it for now. So I guess we can talk about chromatic number of a graph. So, yeah. So the chromatic number is basically, well, you can just read it. So just put it down here. It's the least number of colors necessary so that each vertex of the graph can be colored so that no 2 adjacent vertices are the same color. So for instance, what would be the chromatic number of K3, the complete graph on 3 vertices? So any 2 adjacent vertices cannot be the same color. And you want the minimum number of colors, you need to color it to K color, to color it so that adjacent vertices are not the same color. Yeah, so Cayenne said 3. Yeah, so this is denoted chi of G. So chi of K3 is 3, because if I color this blue, then neither of these 2 can be blue. If I color this green, then neither of these 2 can be, the last one can't be green nor blue, so then I can maybe color it red. So yeah, what about this graph, where what would be the chromatic number of this graph? Yeah, so Adrita says this would be 2, right? Because I can color this any color, like blue, and then the other 2 can be the second color, let's say green. So Alan asks, isn't there some map coloring thing that states it's less than or equal to 4? Well, so that's for planar graphs. So later on, we'll talk about what a planar graph is. So there's a concept of planarity, which is like no edges cross. So for example, you can draw this graph so that no edges cross. You can draw K4 so that no edges cross. Like this is not currently a planar representation of the graph, but you can move one of the diagonals so that it becomes planar. So now you can see, oh, this graph is planar. I can draw it with no edges crossing. So K4 is planar. So for planar graphs, then I think, yeah, the 4-color map theorem says that, you can always color a map with no, like, I don't know. Yeah, with no more than 4 colors. And it was very hard to prove. Like the people were able to prove it in the 1976 with like massive computer like bashing of like 1,700 cases of, how, different, shapes can meet in certain vertices or something. And it was a very ugly proof, and people weren't sure if, it should be accepted as a math proof, even though it's correct, because it didn't make anyone understand the proof any better or the problem any better? Yeah, just make something with 1700 cases and put it on the USUMO. And yeah, no, probably not. Yeah, probably not a good candidate for the USUMO as a problem, and also not a good proof. I think they were able to reduce the number of cases down to like 200 something, but I don't know if there's an actual like easy human understandable proof of the 4-color theorem. So 4-color theorem, you can color a map with 4 colors. So all maps, we're kind of assuming that all maps are planar, but this is actually false for like some weird scenarios. So all maps can be colored with 4 colors if each country is a single color. Assume that, I guess countries are contiguous, and there's some other condition and something else. What's the other condition? So all countries. So like let's say the United States or something, right? If you color every state, each state 1 color, and no state can be the same color as an adjacent state, then the 4-color theorem says you can do that with 4 colors. So, but I think there are some weird things where like maybe part of I don't remember what state it is. It might be Kentucky, where like maybe this is Kentucky, and there's like some random part of Kentucky that's like, I don't know, just on its own island, and then the neighboring state below it just like kind of envelops it. And I don't know, there's some weird configuration where it doesn't work for the US states, because some states are apparently not contiguous by like a very little bit or something. So yeah, but the 4-color theorem just assumes there are no like weird countries where half the countries here and half the countries there, and then you have this other random country and another random country, and maybe this is country A and this is country A, and we don't have like weird disconnected countries. It assumes there's no weird things going on, I guess. But yeah, let's go back to chromatic number, because the chromatic number of a non-planar graph can be bigger than 4. Like, what about K5? What is the chromatic number of K5, for instance? We'll talk about planarity next class, I guess. Or maybe today if we have more time. So K5 just means I connect, 5 vertices. Each vertex is connected to all 4 others. Yeah, so Elias says chi of Kn is just n. Yeah, so so the chromatic number of Kn, the complete graph on n vertices, is just n. Because if I color this with color number 1, then none of the other 4 vertices can be color 1, because 1 is connected to every vertex. If I color the next vertex with color number 2, then none of the other 3 vertices can be 2 or 1, and then so on, right? Each vertex is connected to each other, so everyone is a neighbor of everyone else, except, you're not a neighbor of yourself. So, so basically, yeah, you need 5 different colors, because every, you cannot be the same color as any of your 4 neighbors, and that generalizes for Kn. So it turns out you can prove that K5 is not planar. So K5 is not planar, just to tie in with that previous discussion about the 4-color theorem. I mean, I guess you could state the 4-color theorem and say it's like, you could use the 4-color theorem, but that would be kind of a backwards way to do things, because that's not easy to prove. Yeah, so you can try moving some of the vertices around, but you can never make it planar. Like if I try to draw it planar, I can't connect these 2 vertices with some continuous edge. So that doesn't work, whatever. Okay, so there's also so you can find the chromatic. I don't think there's a necessarily easy way to find the chromatic number of a graph. You can probably like find some algorithms on like what are efficient algorithms to compute the chromatic number, but I don't think there is a general way to compute it for an arbitrary graph, because you could have like very large graphs with very high number of vertices and high average degree, and they could be connected in really random ways. And if there's 1,000 vertices and 500,000 edges, and maybe it's very hard to compute the chromatic number, because there could be lots of graphs with those two properties. So if n equals 1,000 and k equals, let's say 1,000 choose 2/2, or number of edges is this and number of vertices is this, then you could probably draw a lot of graphs with these two properties, and just yeah, it'd be hard to compute the chromatic number of a general graph. But a thing that generalizes this is what's called the I'll call it the chromatic function for now. So chromatic function. Actually, maybe we should compute some more chromatic numbers first. Let's see. It's fine. So we'll just talk about chromatic functions, which I'll rename to something else later. So this is basically, it's like, basically it's like given a graph and an integer k that's positive or non-negative, I guess. How many ways can I color the vertices of the graph with k colors so that no two adjacent vertices are the same color? So this is a function of k. So maybe I should type it out because it's not in the handout. Chromatic function of graph G is the number of ways to color the graph G with k colors so that adjacent vertices are not the same color. Probably typoed. Okay. So this is a function of k because like let's say we have k colors, right? Maybe k equals 5. How many ways can I color the complete graph on 3 vertices with 5 colors if adjacent vertices cannot be the same color? So I'll denote this like P of K3 of K. Well, basically, it's the same problem as before, but instead of finding the minimum number of colors, you're allowed to have k number of colors. So there are k ways to color the first vertex. There are k minus 1 ways to color the next vertex, and then k minus 2 ways to color the next vertex. So the chromatic polynomial for this, this triangle is just this. Well, here it's a polynomial. So this is the chromatic polynomial of K3. So, I can't help it. It's actually called the chromatic polynomial, but it's not obvious that it's a polynomial at the start. It could be some other non-polynomial function, but it's a function of K, the number of colors. Sometimes people will also use like N or X. It doesn't really matter what your input variable is, but it's just basically the number of ways to color the vertices with k colors or n colors so that adjacent vertices are not the same color. So, maybe we should, yeah, so for instance, what would be the chromatic polynomial of like K5? So it's a function of k, and let's just yeah. Well, this is the same as last time, right? So there's k ways to color this, k minus 1 ways to color that, k minus 2 ways to color that, k minus 3, and k minus 4. So the chromatic polynomial of k5 is just this. So what happens if k equals 1? What does this say? Yeah, so Rita says it's 0, right? And does that make sense? So this is saying, yeah, if there is one color, then there are 0 ways to color the whole graph, so the adjacent vertices are not the same color, right? So what this means is, yeah, so Alan says with 0, 1, 2, 3, 4, it's impossible, right? Yeah, so that's exactly right. So we can kind of just say that, P of I for K5 equals 0 for I equals 0, 1, 2, 3, 4. And then by the factor theorem, if I is a root, then X minus I is a factor, or K minus I is a factor. So we can deduce that, maybe I'll just use X, but yeah, so we can deduce that, the polynomial has these 5 factors. It turns out if you have n vertices, then the degree of the polynomial is always n. So maybe if there are m vertices, then degree of the chromatic polynomial of G is going to be m. And it's not obvious that it'll always be a polynomial. So let's do another example. What is the chromatic polynomial of this graph on 3 vertices? So this is the path on 3 vertices. I'll call it P3. So remember, this is a function of, let's just call it x. So this is saying if I have x colors, how many ways can I color it properly? Like, we'll say a proper coloring is, no adjacent vertices are the same color. So how many proper colorings with x number of colors? So this time we're missing an edge. So it's not the same as the last one. So, let's take it one vertex at a time. How many ways can I color the, let's say I start at this vertex. There are, how many ways to color this one? Yeah, so there are x ways to color it. There's no restrictions. And then how many ways to color the second vertex? Well, it can't be the same as the first color, so there are x minus 1 ways to color it. And then what about the third vertex? Yeah, so this time it is x minus 1. It can't be the same as the second one, but it can be the same as the first one. So, and then these are all independent choices, so it'd be this thing equals P of P3 of x. I'll just denote the chromatic polynomial as capital P of, and I'll write the name of the graph if it has a name down here, and then I'll denote the input variable and just denote it like that. So, this accounts for both when these are the same, the first and third are the same, and when they're different. Because, if you want to count it the other way, if all 3 colors are different, there's x minus 1, x minus 2 ways, right? But then we're allowed to have vertex 1 and vertex 3 be the same. So we would need to add in the polynomial. We need to add in a case where they're the same, in which case there's x times x minus 1 ways, right? And then there's 1 way for the third one because it's the same as the first color, the first vertices color, vertex's color. So then when you add these, you just get the, when you add these, you just get x minus 1, x minus 2 plus 1. So you get the same thing as there. So you can do it by case sort too if you want, but that's just slower. You can also start at any vertex, right? So I could say this is the first vertex. There are x ways to color it. And then the two neighbors of the first vertex, they are not adjacent to each other. So there are x minus 1 ways for both of them, because the only restriction is that they're different from the first color, of vertex 1. So what if we have like something a bit harder? And it might be easier to do like a specific example first, but what about if we have the cycle on 4 vertices? What is the chromatic polynomial for that? The Sonak said it's kind of like the generating function for graphs. I don't know if I would go that far, but this is about graph coloring and specifically about vertex coloring. And the type of vertex coloring is where no adjacent vertices are the same color, which is the normal type of vertex coloring you encounter. So yeah, so wait, no, you need casework if the diagonals are the same color, says Adrita. So yeah, let's do a specific example, right? So what if k equals 4, right? Or x equals 4? So what is p? How many ways can I color this with 4 colors? So this is more, standard type of just counting problem. Because the problem with doing it directly, is like if you say, oh, x minus 1, x minus 1, and x minus 1, well, you don't know if these two are the same color. And then you also have to do casework on whether the first color and the second to last color are the same or not, because that determines how many choices there are for the, if I label it 1, 2, 3, 4, the fourth vertex, it could have a different number of choices for the number of colors, depending on whether its two neighbors are the same color or not. So you can't just do it directly by going around the cycle. So, let's just do casework on the P of 4, right? So if there are exactly 4 colors, so X is 4, then, we could use 2 colors, right? We could use 3 colors, and we could use 4 colors. So if I use 2 colors, there are 4 choose 2 ways to choose the 2 colors. And then 2 ways to put, like AA and CC, for instance, right? So there's 12 in the case where we use exactly 2 colors. If I use 3 colors, then maybe this isn't the best way to do it. But okay, so we could, there's 4 choose 3 ways to pick the 3 colors. And then let's see, so we can, there's 3 choose 1 ways to pick which color is repeated. And then there's 2 ways to pick where the repeated colors are on that diagonal or on this diagonal. And then 2 way, well, I think we've already counted for B and C being different. So maybe it's times another 2. So let's see, 4 times. Maybe there's 48 ways. I feel like that's too big. And then if there's 4 colors, then there's just 4 factorial ways, because we can just, if there's 4 distinct colors, so this is number of distinct colors used. Number of distinct colors used total. And then this is the number of ways. So we'll just make this kind of ghetto table here. So 24. So it looks like 84 ways. So maybe let's check doing the other way, right? So there's 4 ways. If we go around the cycle, there's 4 ways there, 3 ways there. Let's say the colors are A and B so far, right? Then case 1 is where the third vertex, it's also A. Then there's 1 way. And then there's 3 ways for this, right? For vertex D, because it's the first and third vertices have the same color. So 4 times 3 times 1 times 3. The other case is if the second to last color is not the same as the first color, right? So A, B, let's say C. Now there's only 2 choices for the last one, right? It could be D or it could be B. So there's 4 ways times 3 ways. And then this color, it's either, well, it can't be B, it can't be A, it's either C or D, because it's not the same as the first color or the previous color, B. And then there are 2 ways right there. So 4 times 3 times 2 times 2. So let's see, this gives 36, this gives 48. When we add it up, we get 84. Okay, so 84 is probably the answer to this type of problem, to this problem. So, whatever our polynomial is, if we plug in 4 into it, we had better output 84. So that's a good check. I think we can generalize our work that we did here, right? So let's compute so let me just type this out. Compute the chromatic polynomial for C4. Okay. So, I guess we just repeat the reasoning, right? So in case 1, the color of vertex 1 equals the color of vertex n minus 2. Let's just do vertex 1 like that. So that means there are, let's use the variable, let's just use n, okay? So n is our input variable. So there's n ways to color the first vertex, n minus 1 ways to color the second vertex. This third color is the same as the first color. So if this is A and this is B, then this is also A. There's no choice on the third vertex. It has to be the same as the first vertex because we're in that case. And then there's n minus 1 choices there. So in case 1, we get n like that. And then, so that's case 1. And then we have to add the other case where the case 2, so color of the first vertex going around the cycle is not equal to the color of the n minus 2 vertex going around the circle. So this time there's n ways, n minus 1 ways, n minus 2 ways. So let's say this is A, this is B. This one can be neither A nor B, so it's C. And then there's n minus 2 for the last one. Let's call it D. So we have to add in case 2 where there's n minus 1 choices, n minus 2 choices squared. So let's see what we get. It looks like it's a polynomial because we're adding 2 polynomials. So plus something, okay. So we factor out the n minus 1, and then we have an n minus 1 plus n minus 2 squared. So that's n squared minus 3n plus 3. Yeah, so this is a chromatic polynomial. So it's kind of interesting because, here we have like, not nice roots. So here we had to do casework on whether, if we were doing the chromatic polynomial with a 5 cycle, we would have to do the same thing. If I go around the circle, considering each of these colors, I'd have to do, are these two the same color? If this is the first color, second vertex, third vertex, and fourth vertex, and fifth vertex. And then to figure out if these two can be the same vertex, same color, I need to do casework on whether 1 and 3 are the same color as well. So it's not super easy, even for this like small example, it's not like extremely trivial to find the chromatic polynomial. And let me just check, right? So P of 4 times 3 times, what's 7? Yeah, that's 84. So yeah, it should be the same because we did the same reasoning, but so yeah, this generalizes the problem of how many ways there are to color a graph with n colors. Let's check, right? If n equals 1, P of C4 of 1, then it's 0, right? There are 0 ways to color it with one color. If we plug in 2, let's see, this says it's 2 times 1 times 1. So there's 2 ways to color it, right? And that matches what we said before, right? Because you could have A, B, B, or swap the diagonals, A, B, B, A, A. So B, A, B, A, like that. If I plugged in 3, do I get the right value? You can check that, you probably do, but maybe we'll just check it. So 3 times 2 times 3 is 18. I'm a little bit lazy to compute if this is correct, but you can check that, it'll be correct. If there's 2 colors, then there's 6 ways. If there's 3 colors, if you use 3 distinct colors, then yeah, I think there's 12 ways. So we'll get 18. You can just do some casework and check. 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 So, one question is, will this always be a polynomial, right? Because, here we had some weird stuff, which, n squared minus 3n plus 3 is not really expected at the very start of the problem. So, it turns out, what I originally called the chromatic function. So, theorem of the chromatic. Well, I typed it here, so I'll just paste it over. So the chromatic function of a simple graph is always a polynomial. It turns out there's like a recursive way you can compute this. But just as a reminder, a simple graph means like you don't have multiple edges between the same pair of 2 vertices. So that's not allowed. And you also don't have self loops. So you can't like have an edge with vertex with both endpoints at the same vertex. But you can't have disconnected graphs. That's allowed. That's simple graph. That's a simple graph. So simple means no multiple edges, no self loops. So there's this theorem called like the vertex deletion contraction theorem. Yeah, sure. Let's go with that. So basically what it says is, if you have a simple graph, then let's say I want to find the chromatic polynomial of this graph, right? So let's say it's like the complete graph on 4 vertices, but you remove a diagonal. So it's missing this diagonal. So what this theorem says is the chromatic polynomial of this, so P of this thing, is equal to oh, I didn't copy the whole thing. Let's see. Or I didn't write down the whole thing. But basically, it's going to be the chromatic polynomial of the thing without the missing edge minus the chromatic polynomial of so there's this concept of contracting two vertices. So, if I have, let's say, this complete graph, so this is vertex contraction. Deleting an edge is, clear what that means, but contracting, I can't. Contracting. So contracting just means, let's say I want to contract this edge. That means I move vertex B onto vertex D, and I just make the edge shorter and shorter until it disappears, until B equals D. So after the contraction, this graph will look like, this is B equals D, and then you have the other 2 vertices. And then you don't remove any of the edges. So there's a double edge between C and the contracted vertex and D there. Yeah. Okay, so let's see. Yeah, so this would be, the complete graph on 4 vertices, but with B and D contracted, like the edge between B and D contracted. So that's what this means. So this should say P of So this should say P of G minus E plus P of G contract E. Oh, sorry, G contract E. So normally the way you apply this theorem is if you're missing an edge, you do the chromatic polynomial P of the thing with the edge still there, and then you minus the thing with the edge contracted. So it'd be minus the chromatic polynomial of this graph. So if I want the chromatic polynomial of this graph, let's just denote it like this. Then I'll just say, oh, this is for K4, it's just this. And then for this missing thing, let's compute it. I think it's the same as, so minus K, K minus 1, K minus 2. It's the same as K3, the complete graph on 3 vertices, except you have some double edges which don't affect the chromatic polynomial. And I think maybe, yeah, it should be pretty doable to, let's see, why is this true? Maybe we should think about why it's true. But at any rate, if we compute this out, we'll have K, K minus 1, K minus 2, and then K minus 3 minus 1. So, oh, wait, hang on. Yeah, so that's just K minus 4. Let me look at the notes, my notes, and see if that's. Sure, we'll go with that for now. So, let's see if we can prove why this is true. So this is like you have any graph, And so supposedly it's the sum of the chromatic polynomials of, if you delete this edge. So if you delete that edge, which is denoted G minus that edge, and then the chromatic polynomial of G contract, or I think this is like vertex edge contraction. So this is where you contract the edge, so it looks like this. Sure, I drew in the wrong orientation, but yeah, basically B and D get contracted to be a single point, and you don't remove any edges except the one between B and D. So that's B equals D, that's A and C. So let's see, I think this is just casework. So if I do the case where, let's see, yeah. So let's say we contract AC, right? So we contract or delete AC. So if the color of A, let's just denote it C of A, is the same as the color of vertex C, then which case would that be, right? So, if they're the same color, that would be when we delete the edge, I think. Or is it when we contract the edge? I guess it's when we contract the edge. And then when we delete the edge, like if this edge was still here, if this red edge or blue edge was still here, then vertex C and vertex A have to have different colors. So, if vertex A and vertex C have different colors, then it would be, the chromatic polynomial of G minus E. If they have the same color, that would be the chromatic polynomial of G, contract edge E. So same would be P of G contract E, or delete E. I mean, contract E, sorry. So yeah, those are the only two cases. And you can check that, when they're different, it's the same chromatic polynomial as if you took the graph G and removed the edge. If the two endpoints of the edge we're removing have the same, are the same vertex, then that's, the same as like if you contract that edge, that's the number of colorings for that graph. So those are the only two cases. So this is true, and you usually rearrange it to apply it so that you usually isolate this and use subtraction or something. So usually it's written like P of G minus E equals the other one minus this one. That's how we used it above. So yeah, with this, you can prove that all graphs have their chromatic function is actually a polynomial, because it's just one polynomial minus another. Like if I have any graph, right? If I have any random graph, I can always start off with the complete graph on n vertices and just keep subtracting edges off and deleting edges and contracting stuff until it becomes the graph I want. So you can always do a recursive proof to see that the chromatic function is always a polynomial for any graph. Let's see. So let's just look at a few examples again. So let's see. So, what would be, let's go back to easier questions. Like, what would be the chromatic polynomial of this graph with no edges and 3 vertices? Well, there are no edges, so there's no restrictions. So yeah, Cayenne says x cubed. Yeah, that's right. So we just have x choices for each vertex. And then let's just do, now what about this graph? Well, here there is, so let's call this G2. So yeah, there's x choices here, and x minus 1 choices there. So it's x squared, x minus 1. Let's do the other, what about G3, where it's this again? Oh, well, we already did this. It was x times x minus 1 times x minus 1. And we already did the complete graph. I'll call it G4. This was x minus 1, x minus 2. So let's look at these 4 examples, right? Are there any observations you can make? I'll expand it out. So Drita says, as you add edges, you subtract 1 from one of the 3 numbers you're multiplying. Okay. Well, so, that's true in this case. But remember, when we had the other case, like, here, if we have the complete graph on 4 vertices, this is k, let's use x. X minus 1, x minus 2, x minus 3. So it looks like that. But when I deleted the 2 of its diagonals, it looked like x minus 1, x squared minus 3x plus 3. And this has no like integer roots, right? So that was the chromatic polynomial for this cycle. And I'm not going to multiply it out, but you can multiply it out if you want. So, it's not really clear what I'm asking, so I'll just say what I'm kind of looking for. One thing is there's no constant term, right? So, and why is there no constant term? Oh wait, is it even obvious why there's no constant term? Let's see. So Sonax says, because x equals 0 gives a value of 0. Yeah, right. And Cayenne says, because all the colorings are dependent on x. Yeah, I mean, it kind of makes sense that there should always be like you can choose any one of the 4 vertices to be the first vertex, and then there's x ways to color that. But I think the better way to see it without using that, because it could be very asymmetric, right? You could have like some graph that looks like this. And or maybe it looks like this, and I don't know, it just there could be like lack of symmetry. So I think the clearest way to see it is if I plug in to find the constant term of a polynomial, you plug in 0 usually, right? That gives you the constant term of the polynomial. But if there are 0 colors to choose from, then there are 0 ways to color any graph with like a positive number of vertices, right? As long as it's not the empty graph with 0 vertices. So yeah, P of 0 should be 0. So that means the constant term should be 0. The other thing to notice is, let's say I add up all the vertices, all the coefficients, right? Like, hang on, so let's say, in this bottom one, 1 plus -6 plus 11 plus -6, the sum of the coefficients is 0. The sum of the coefficients is 0. Sum of coefficients is 0. Why is that the case? So 2 sum coefficient of 0. So yeah, how do we usually get the sum of the coefficients of a polynomial? Well, yeah, so Kayan said, yeah, you plug in 1 into the polynomial. That gives you, the sum of the coefficients. Like, if this is our polynomial, if I plug in 1, then I get the sum of the coefficients, because that's when you let all the x's be 1s, and that'll be exactly the sum of the coefficients. So, and 1 is always a root, right? So P of 1 is 0. But I mean, 1 isn't always a root. I mean, the only exception was this one, right? Here, 1 was not a root. Why was 1 not a root in the first graph? So here, the sum of the coefficients is actually like 1. So Eli says there are no connections. So yeah, if we have, so this only applies if number of edges is at least 1, right? If you have 0 edges, then this doesn't apply. But if you have at least 1 edge, then the sum of the coefficients is 1, because you'll always have like, an x times an x minus 1 or something if you have just one connection. So, I guess, basically P of 1 is 0 because, there are 0 ways to color 2 connected edges or 2 connected vertices with 1 color. So if there's 1 edge, you can't color it with 1 color. It needs at least 2 colors to properly color it. So that means sum of coefficients is 0 if there's at least 1 edge. Okay. Another thing you can notice about these is, what do you notice about the x squared term, or the second smallest coefficient? I mean, like if it's degree n, what do you notice about the x to the n minus 1 coefficient? So Kayan says negative. Yeah, it is always negative. Is there anything special about the number in relation to the graph? Number of edges? Yeah, it looks like, it's the number of edges. So, here there are 0 edges, so it's minus 0x squared. Here there's 1 edge, so it's minus 1. There's 2 edges in G3, this is a 2. There's 3 edges in G4, so this is a -3. There's 6 edges in K4, so this is a -6. There's 4 edges in this graph, which is a cycle. If I multiply this out, I'll get, so let's see. I'll get something like x to the 4th minus 4x cubed plus 6x minus 3x, or 6x squared minus 3. So this thing becomes this thing. 6x squared minus 3x. Okay. So yeah, 4 edges, we have a -4 here. So why is this true? Let's see. So let's just make this as a conjecture for now. And if we have time, we can come back to it. But I'll just leave it as a homework thing to think about. The coefficient k sub n minus 1 of x to the n minus 1 is, let's call it a sub n minus 1, is negative the number of edges. So there's also one other observation we can make, which is like, it looks like, all of these coefficients, they alternate in sign, right? Positive, negative, positive, negative. So conjecture the coefficients alternate. And this isn't super obvious because, there was that one weird one that we worked out, which was like x times x minus 1 times this, right? X squared minus, it's not super obvious that this will alternate in sign. So that's another thing to ponder about. From the alternating signs conjecture, I think you can prove by Vieta's since the roots should always be positive. So additional trivial homework, Collat's conjecture. Yeah, basically, I'm just like assigning all these things that I don't know as homework. So yeah, or there are things to think about, and there's things you can read up in the graph theory literature that's like, doable, I think. So I'm not so sure about it's obvious that all the roots are positive. So there is, I think I did read, so there is one cool theorem, which is, so let's see, all real roots of a chromatic polynomial of G other than 0 or 1 are greater than or equal to 32 over 27. So it doesn't say anything about complex roots, but yeah, this is the theorem from, I think it was from Wikipedia. And I already did it. Okay, so yeah, so, no graph can be 0 colors, so 0 is always a root. Chromatic root just means like a root of the chromatic polynomial. Edgeless graphs can be 1 color, so 1 is a chromatic root of at least 1 edge. And then other than those 2 points, no graph can have a chromatic root at a real number smaller than or equal to 32 over 27. So this is like an interesting theorem because, where the heck does this number come from, right? It's like very weird and random. So, maybe let's check. What are the roots of this? Are they even real? So, oh, they're not real. Okay. Yeah, maybe I should link where I saw this so that you can read about it on your own too. Yeah, so if you look right here, if you look under like the chromatic roots part, it says this, wait, where did it? Yeah, it says something about the 32 over 27 number. It doesn't say anything about the non-real roots, but the real roots seem to satisfy this theorem. Yeah, I mean, maybe the real root, maybe it comes from 2 to the 5th over 3 cubed. Yeah, I haven't read enough into the literature to know why this is true, but I've heard it from multiple sources. So, I have good confidence that it is true. Let's see. Oh yeah, so another thing we can ask is, let's say we have 2 graphs, right? And maybe they're not isomorphic. So they're not the same shape and structure. So can you have like 2 non-isomorphic graphs have the same chromatic polynomial? So just as a reminder, last time we said something about this graph being not isomorphic to this graph, because the second graph is called the Peterson graph. It's got a lot of cool properties. And the reason these two weren't isomorphic is because the shortest cycle was 4 here, right? You have a cycle of length 4, but the shortest cycle in the Peterson graph has length 5. So both of them have 10 vertices. Both of them have like, 15 edges. Each of the 10 vertices has degree 3. So that's called a cubic graph. So that's 3 regular, but they're not isomorphic. So just because all 10 vertices, each of the 10 vertices has the same degree, doesn't mean the two graphs are isomorphic. So let me catch up on what you guys said in chat. Okay, so Adrita said, yeah, they could have the same number of vertices and edges. Yeah. So yeah, maybe it's not super clear how to think up of such graphs. So let me just show one example. So let's say we have this graph, right? So it's 4 vertices. This is a claw graph because it looks like a claw. I'll draw it like a claw. And then what would be the other one? Let's say we have the path graph, right? So these are clearly not isomorphic because one vertex has 3 connections here, degree 3. This one has 2 of degree 2. So they're clearly not isomorphic. They're not the same shape if you move the vertices around and keep the connections between the same pairs of vertices the same. But let's check, right? This one has chromatic polynomial. There's x choices there and x minus 1 choices for each of these. Let's check this one, right? There's x choices here, x minus 1, x minus 1, x minus 1, because each one has to be different than the previous one, for when we choose the next color. And we could have chosen them in a different order too, right? Like there's x choices here, there's x minus 1 choices there, there's x minus 1 choices there because it's different from that one, and there's x minus 1 choices there if these are like connected like that. So at any rate, these have the same chromatic polynomials, that and that, but they're not isomorphic. So here's another picture of 3 graphs that are not isomorphic from Wikipedia. So these 3, they're all different, but they have the same chromatic polynomial. Okay, so there's a lot of interesting there's a lot of interesting things. I remember I took a course with Richard Stanley at MIT. He's a professor emeritus there now, so he's like not there anymore. He kind of retired, but I think he proved when he was younger that he proved that there's something special about the x to the n minus 2. It was either I think it was the x to the n minus 2 coefficient, or maybe it was the x coefficient of the chromatic polynomial. Like it was always something to do with the number of cycles in the graph, a certain type of cycle in the graph. But I don't remember the exact statement of the theorem anymore because I don't really work with these that much. So, but you can definitely read up on it, and I'll try to find it after class and maybe link it in an email. So I guess we can go on with okay, maybe we'll let's see. Actually go out of order. You know what? How about let's just turn it into an open office hours. Do you guys have any questions you want to ask me? It doesn't have to be math related, but you can just ask me random questions because my voice is too tired to talk too much about math tonight. So yeah, if you have any questions, you can ask me. Else, we can either work on a problem together or we can adjourn for today. So, just gonna... Can we work on an example problem from graph theory that came from some contest? Yeah, that wouldn't be a bad idea. Well, I remember I collected a few of those. Let me see. Give me a sec. I'm picking this question out of over the other ones because it's actually related to the topic. So I'm giving preference to this question. So let me see, one sec. Where did I put the graph theory problem? I remember there was this yeah, here it is. So probably some of you who have been working very hard on AMCs have seen this before, but let's just take a look at it. So this is a computational graph theory problem. There's lots of graph theory problems that are proof-based that are like just on, it can be on Olympiad or just in the graph theory literature, but it's kind of hard to make a computational graph theory problem, but you can do it. Yeah, I'm sure some of you have seen this before. So let's say we have like vertices A, B, C, or let's not draw any like edges yet. So because mathematicians are so unlazy and creative with their namings, their names start with A, B, C, D, E, F for my convenience. So no, not really, but I find it kind of amusing. So some, but not all of them are internet friends with each other, and none of them has an internet friend outside of this group. Poor them. Each of them has the same number of internet friends. How many ways can this happen? So, yeah, it might be like a late like AMC 10 number 23 or like AMC 12 number 23 or something. So it's actually a bit time consuming to put it on an AMC in my opinion, but so let's make sense of this, right? So we'll assume that being internet friends is mutual, meaning if A is a friend of B, then B is a friend of A. So let's see. So some, but not all, right? So some means the number of edges is at least one. Not all means the number of edges is not like it's not the complete graph on 6 vertices, right? So it's not like everyone has at least has exactly 5 friends. So it can't be the complete graph and it can't be the empty graph. So not empty, not complete. So then it says each of them has the same number of internet friends. So that means it's R regular, right? For some R, and R is not equal to 0 and R is not equal to 5, or else it'd be complete or empty. So, each person can have 1 friend, or everyone has 2 friends, or everyone has 3 friends, or everyone has 4 friends. So how many ways if everyone has 1 friend? first off, what would that look like again? Remember, it doesn't have to be connected. Yeah, so Cayenne says 3 pairs, right? So, you could have them pair off with each other. Maybe it's like girl, boy, girl, boy, girl, boy, or, well, it doesn't have to be, any sort of dance pairing or something like that, something silly that school makes you do in PE class if you're doing dance. But yeah, yeah, so it could be like this. What if, let's draw the other cases before we can, well, so let's just compute this. So how many ways can you pair up the 6 people into 3 pairs? So let's see, if I take any one random person, let's say person A, there are 5 ways to choose person A's partner, right? Then there's 4 people left. I choose any one of the 4. And there are 3 ways to pair up, the 3 remaining people with that 4th person, right? So once I've chosen A with F, for instance, and B with, let's say, E, then there's only 2 people left, and there's only 1 way to pair them up. So it's 15. Another way you can compute it is just 6 choose 2, 4 choose 2, choose 2. But you need to correct for overcount because, I guess, it's like you've overcounted by 3 factorial and maybe some powers of 2. So this is 15 times 6. And we could have chosen the first pair first, or the first pair last, or the first pair second. So there's 3 factorial ways to kind of. So either way, we get 15. So what about case 2? So it's 2 regular. What could it look like this time? Let me just make sure the problem statement is, Yeah, so it can look like a hexagon. Is there another way it could look like? What's another structure the graph can have? Yeah, so Sonak said 2 triangles. Yeah, exactly. So is there any other ways for it to be 2 regular? Yeah, we can't have like a 4 cycle and a 2 cycle because, well, a 2 cycle is not simple. And yeah, this is the only way basically, but these are the only 2 ways. So how many ways can we do it? How many ways can we have a 6 cycle? Remember, it can be any order, and the edges crossing doesn't mean you form a vertex. So you could go like that. Oh, I didn't draw the cycle right, but you get the idea. Do. It could be something like that. That's a 6 cycle. Yeah, so there's 5 factorial. Normally there's 6 factorial ways, but you could start at any one of the vertices. And so it's 5 factorial. Or you could just pick a person at random and say there's 5 factorial ways to go around the cycle. But have we overcounted, or is this it? Like if I have a 3 cycle, is the answer 2 factorial? Or is the answer 1? Why is the answer not 2 factorial? If there's a complete, like a cycle of length 3. Because it looks like there's only one way to draw a triangle with 3 vertices, right? So yeah, does anyone want to say? Yeah, so basically, let's say I pick the path A, B, C, D, E, F, right? I can cycle this any one of 6 ways, so I need to divide by 6. But this is the same path as A, F, E, B, D, C, C, B, right? I could also go this way around the cycle, or I could go this way around the cycle. So I need to divide it by 2. Because I could count the path going around the cycle in clockwise or counterclockwise. There's 2 ways to go around it, and it would be the exact same cycle both ways. So if there's 3 vertices, A, B, C is the same cycle as C, B, A, which you can rotate to be A, C, B. And all 6 permutations with 3 would be the same. So yeah, we need to divide by 2, so it's 120 over 2. What about 2 triangles? How many ways then? $24. Pick the 4 factorial. Nope. Then, so there's nothing special about the orientation. I could have drawn the triangle like this. I could have drawn the triangle like this. So okay, here's one way. Here's a question: is it 6 choose 3? Is that the number of ways to pick 2 triangles? I mean, well, I guess you could times 3 choose 3 for the second 3 points, but that doesn't matter. Or is that wrong? Yeah, so Eli says, we need to divide by 2, right? Because if I pick A, B, and C to be my triple, that forces D and F to be the other triple. But I could have picked D and F and got these same 2 pairs of triples, right? So I've overcounted by a factor of 2. The other way to think about it is I pick a random person A. The 2 neighbors in the triangle of person A, there's 10 ways to choose it, right? 5 choose 2. Once I've chosen the 2 neighbors of A, they make a triangle, and then the other 3 are forced to be. So you could just say 5 choose 2. In fact, this gives a combinatorial proof that, like n, 2n choose n is twice of 2n minus 1 choose 2n n minus 1 or something. We just proved combinatorially that this is true in general with a specific example. Okay, so there's 10 ways here. So we had 60 plus 10, which is 70, right? So you get 70. And then we had 15 here, right? In the first case. So now we have 2 more cases, and it seems like they may be hard. But what's nice about the r equals 3 case and the r equals 4 case? So Arrowhead says just multiply by 2. Yeah, why can't we just multiply by 2? I'm assuming you mean like you add the previous 2 numbers and you multiply that by 2. By symmetry? Yeah, so what kind of symmetry do you mean? So maybe not everyone sees just yet. Like how are the r equals 3 case and the r equals 2 case related? Yeah. So, when you say symmetric, you need to kind of describe what the symmetry is, because there's lots of different kinds of symmetry you can have, right? You can have rotational symmetry, you can have permutational symmetry, you can have like, it's not super clear what you mean by symmetric. In fact, there's a better word for it in the language of graph theory. So here, I guess I'll just say it since you may not know the word, even though I mentioned it earlier. So if I take any cycle, right, or any of the previous graphs, right, I can take what's called its complement. Yeah. So the complement is just anytime there's an edge in the original graph, you don't have an edge. If you don't have the edge, then you do have an edge in the complement. So for all pairs A, B, swap whether there's an edge between them or not. So here you would just have like these 9 diagonals. Instead of the 6, like kind of the edges, what I drew as the edges of the hexagon. Here you would just have, you would have this, this, and this. You would have that, 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 and that. So you have all the empty edges, which are marked in green, instead of the edges of the original. Just like if you have like this case, you would just you remove the blue edges and connect every other like not connected pair of edges. So that's the complement. So for each of the 70, 2 regular graphs, there's a corresponding 73 regular graph if you take the complement of each of those 70 graphs. And same for case 1. So you can just double our previous number. It's 70 plus 70 plus 15 plus 15. Okay. So in case I forget to include this in the Dropbox folder, these were just some of the problems I found on computational contests that were graph theory related. You can probably find some more on HMMTs or like, obviously the Olympiads can have graph theory problems, but yeah, these were just some that I noticed from previous years that I kind of compiled into a document. So I'll try to. So yeah, I think we'll stop here for today. Next time we'll probably talk. Yeah, we'll probably do more graph theory, even though it's there are some there are some Olympia problems at the end, but we'll just go over the actual theory part of graph theory because it's interesting, cool, and useful. But you can work on Olympia problems on your own because those are a different flavor, and I have nothing against working on them in class, but I think it's more beneficial just to see some of the basic theory of the different branches of graph theory at first, rather than jumping into hard problems that are like super tricky or very clever to find the solution. You need to be very tricky or clever to find the solution too. Okay, so yeah, for those watching on YouTube, that's the end of today's lecture. Have a good week.